you need to read and understand the parts of Chapter 8 that we are covering, okay? But I do apologize. I want to try to shift back. By Monday, I want to assign homework for Friday so that the recitation is more useful. I would still encourage you to go to the recitation tomorrow, in preparation for the homework, but it's posted. Yeah?
On the syllabus says exam next Friday, is that going to be pushed back to?
I'll have to think about that. I'll have to think about that. Yeah, because if I do have the, yeah, that's right. If we have the exam Friday, then of course I won't have homework next week. But I think, I could tell you now I'm probably likely to push the exam back. But I'm going to have to think about that. Okay, so that's working. Good. All right, where were we? I had, talking about two particles. These ideas can be generalized to more than two. The wave equation for the two particles, we essentially try separation of variables again. We separate it into wave functions for the two particles. The two wave functions multiply each other. I wrote that down on Monday when we got to here. And then I divided by psi1 times psi of x1 times psi of x2, and I get to this point. Unless U sort of talks about an interaction between the two particles, and in particular, let me do. We're now going to look at a. Let me not write that there. Let me write it here. In particular, if we look at a particle in a box. Where in the box U is 0, we then have this situation. And this is familiar, right? This is the same idea we keep having when we separate coordinates. This better be some energy for the particle number 1. And that better be some energy for the particle number 2. And those sum to E. Simply because this being a constant, whatever particle 1 is doing is independent of what particle 2 is doing, so this term and that term must each be constant. Otherwise, there's no way when I sum them, I continue to get a constant, right? And of course, remember, I don't mean x1 as one variable of x and x2 as another. Both, it's just a single one-dimensional particle in a box where this is x. I stuck the label for particle 1 on the x. And the label for particle 2. Both particles are in the same box in one dimension. Okay? So pretty straightforward. And then obviously, if this is equal to E1, then I have the same, wave functions, Schrodinger equation as I had before for each of them. And there's a similar equation for particle 2. All right, so nothing hard here. I'm just introducing the notion that I should have the two particles and that their wave functions should multiply. All right, and then they completely separate out. So for instance, I can write, let me erase my box. This is equal to E. Let me try to get off this yellow chalk. So just to be simple, well, I'll simplify in a second. So I can write that the total combined wave function, which I wrote as the product wave functions, the total combined is psi of x1 times psi of x2. We know what the solutions to these are like, right? This is just, again, the particle in box. And those are root 2 over L. I'm multiplying the two of them, so I'll square that. Sine n1 pi over L x1 right? That's all it is. All right? So there's a way to think about this. If I take n1 equals 1 and n2 equals 2, and then I think about p of x1 and x2, which is psi squared, or I should write the complex conjugate squared, although this is all real. Okay? So let me just plot p. If I work in the x1 direction, if n1 is 1, then this was the thing, it was just a half hump, a half wave going from 0 to L. If n2 equals 2, going from 0 to L, right, that was a whole wave. So basically, I'm going to get a probability distribution. Going in this axis, I'm going to square it. Psi would look more like that. The probability of the square will look more like that. So it's going to look like sort of two areas of concentration and probability plotted on this graph, which is not really a physical plot, right? I mean x for both of them, but it's just, there's this kind of combined idea, right? And so for instance, the note that the probability that x1 equals 1/2 L is, it's actually the maximum. That's the most likely probability for x particle 1, is that it's in the middle. Notice that the probability that x2 is in the middle is 0. This is nothing special. This is exactly the features we had for the particles in a box. But you know, it's just sort of a combined thing. Okay? Straightforward? Now, there is a twist. This was too easy. Okay? The mathematics isn't going to get any harder. It's because this is straightforward. But there's an interesting fact that happens in quantum mechanics. And the thing that happens in quantum mechanics there's just a completely new idea. Particles, well, I should put identical particles. So identical means 2 electrons, 2 protons, 2, you know, Siamese cats, whatever, if they're the same thing, are indistinguishable. Now that's a new thing. I don't mean like if you have identical twins and you can't tell them apart, right? You could ask them and they could tell each other apart, right? Indistinguishable in quantum mechanics really means at a very fundamental level, there is no way to, well, distinguish one particle from another. Mathematically, it means I can't write down a wave function for 1 and 2, which leads to a probability for 1 and 2 that is any different if I switch 1 and 2, if I switch the roles of 1 and 2. Okay? So basically, mathematically, this doesn't work. Because simply put, I had, this was all just really straightforward, right? I did as straightforward as I could, and I end up with something that doesn't seem at all contradictory. I have the notion that particle 1 is peaked right here, and particle 2 is peaked here and is 0 right down the center there. That's straightforward. But if these particles are the same, this falls apart because I cannot, these I distinguish. If you ask me to pull out, particle 1 here and not grab particle 2, I could do it. I would grab a particle, remember this is the same box, I just made this funny plot of a probability distribution. If I grab the particle, if I go in and grab a particle at exactly half L, I can only pick up particle 1 here. There is no probability that particle 2 is there. And yet we have this notion from quantum mechanics that you cannot distinguish 1 and 2. I literally can't put a label on 1, I can't put a label on 2. If I was filling the box with an electron, it means that it's like after I put the first electron in and I put the second electron in, I can no longer distinguish them, but in a really fundamental way. It's not because I put the first one in and I was watching it, and then I put the second one and I took my eye off the ball and I didn't see them rattle around a bit and I kind of got confused. It's not like a shell game. It means that basically you can't even ask the question. If there's 2 electrons in there, you can't ask a question which distinguishes one from the other. Yeah?
So you're kind of saying that at 1/2 L, if you were to look, you would find, rather than saying you find particle 1 and not particle 2, you would find a particle and not L. Is that how it works?
Sort of, yeah. So in fact, this looked really straightforward, and what could be wrong with this formulation? Well, it turns out there's just a simple fix to this formulation, okay? The simple fix to this formulation, well, let me explain exactly why I don't like this formulation. What I really wanted to do then is this first x1, it was just like the first particle, x2 was the second particle. What I want to do is mathematically what I want to do is I want to establish the principle that if I try to switch the role of 1 and 2, that I get the same answer, okay? And that would be to say that they're indistinguishable. Suppose I tried to number them, and you let me try, and I did it. I'm going to say, okay, fine, I don't care if you did it. It's the same as if you labeled them the other way around, right? That's indistinguishable, okay? So, the way I want to write it is this. So psi of x1 and x2, I'm going to write just simply as psi of x1 particle state 1. Okay, so this means state number 1. And okay, I'm not going to just drop the label on the particles. I don't want to do that. Then I don't have anything. Then I can't write anything. But I want somehow the labels not to mean to not allow me to actually effectively label them. Okay. So, question? So I put a subscript here. The book uses n and n prime for this. I'm going to put a number there, but it's the same idea. So I put a state number 1 for particle number 1, and this is state 2 for particle 2, right? And what I'll do is I'll add to that particle 1 was also in state 2, and particle 1 was also in state 1. No, sorry. That's why I had to look at my notes. Very simple. I'm just going to be playing with subscripts, but I'm going to mean a lot. I wanted to be very careful and not make a mistake, which I just did. But so state 1 of particle 1, state 2 is what particle 2 is in. 1 and 2 might be the same state. They might be different. Over there, I use the example of n equals 1 for state 1 and the n equals 2 particle in a box state for particle 2. But in general, I mean any state in quantum mechanics which has a number associated with it or a label, okay? Then what I'll do is I'll just add the same thing, but I'll flip the roles of states 1 and 2. Okay? So what I really mean is before I squared this to create the probability, which is what I graphed, I'm literally going to take this and I'm going to add the reverse. And I'm going to get some more complicated thing when I square it that is no longer going to have this property that I can distinguish one particle from the other. All right? And that's what you have to do. And this sounds bizarre, and it is bizarre, but it's just the rules, and it is what matches the data. If you don't do this, then quantum mechanics doesn't match life. Okay? This is what has to happen in order for quantum mechanics to match what we've measured. Let me just erase all this. And in fact, that wasn't the only way I could have done it. Let me just rewrite what I just did. So psi, I'm going to put an S here, which I'll explain in a second. This one is psi 1 of x1 times psi 2 of x2. I need more space. I sort of wanted to leave this graph up for a second. Plus psi 2 of x1 times psi 1 of x2. So, and let me explain a second, what do I mean? So by reversing particle, by switching particles, okay, it means just interchange x1 and x2. And if I do that, if I put that there and that there, and I do the same here, if you start this a second, can't you see that these two terms just switch places? Okay? Right? So if I put x2 here and x1 there, then I have psi 1 and x2, and that's the same as what I had here. And I have psi 2 and x1, and that's the same as what I had, sorry, psi 1 of x2 I had here, and psi 2 of x1 I had here. So this term will equal the old that term. Similarly, if I put x2 here, I'll have psi 2 of x2, and if I put x1 here, I'll have psi 1 of x1, and so those are just these. So if I reverse 1 and 2, this piece turns into this piece turns into that piece. Nothing changed. So I've met my requirement. I've said, fine, you can try to label these, but this little trick makes it such that the label doesn't really help me distinguish them. Now, I said that that's not the only way to do it. Very simply, I could have done the same thing I could have subtracted. I could have subtracted them. I could have subtracted the wave functions. Okay? Here, psi s of x1, x2 equals psi s of x2, x1. That's what I just argued. I mean, I could write it down, but it's just tedious. I keep writing and writing, and I'm doing a simple thing. Here, if I switch 1 and 2, this will become psi 1 of x2, which was that bit. And this will become psi, and I forgot my label here, psi 2 of x1, which is that bit. Similarly, that will be the same as this bit, but there's a negative sign between them. I think you can see that, I hope you can see that psi a of x1, x2 is minus psi a of x2, x1. Okay? Does that make sense? I'm doing pretty simple things here with math, and it's easy kind of to say, okay, just follow me. But you're going to, it's a little bit subtle. So is everyone with me? By the way, has anyone seen this stuff before? One of you. Yeah, I didn't think you would have seen it, unless you've had some advanced or more advanced class in any of this. What does the S stand for? S was symmetric. This is antisymmetric. That's what the A is for. So it's a simple idea. Remember, when we look at a probability, because the probability is the real thing we worry about, we're always squaring the wave function. And so the probability in the antisymmetric case, you might say, because I get this negative sign, oh, wait a minute, if I switch 1 and 2, I'm not getting the same as if I had, as I originally had. Well, no, I picked up a negative sign, but there is no physical meaning to the wave function alone. In any situation, I actually have to square it. And when I square it, the negative sign is gone. So both of those meet my indistinguishability requirement. Okay? Yeah?
It looks like the math is kind of implying that the state of one particle affects the state of another in that box. Is that what's happening?
Say that again, a little louder.
It's like it's implying that the state of one particle is affecting the state of another.
The state of one particle.
The state of the other in the box.
Why would it?
I don't know, because you have the. Sorry.
No, that's a reasonable thought. You're saying by adding them, I'm having the two particles sort of affect each other?
Yeah.
Well, you're not wrong at all. I mean, there is something funny that happens, okay? I mean, okay, clearly I've modified the wave function. I've sort of done, there's a part of quantum mechanics, there's the part we've gone through so far, which was good for making an exam problem and a test problem on, which was, let's solve the Schrodinger equation. It can get really hairy and there's lots of stuff, and let's find an average, and you guys have to go find an average, right? It's all straightforward, okay? There's a part of quantum mechanics where it's almost like sorcery. I'm writing some things and I'm writing a lot of subscripts, and I tell you some rules, and then we start playing with the subscripts, and suddenly it's all gone topsy-turvy, even though I didn't write anything down hard mathematically. And this is that case. It just turns out that this bizarre thing, I remember this really bothered me when I first heard about it. The professor said you can't make one electron red and one electron blue. They're all the same color, some fundamental way. Mathematically, I don't know if there's any other way to achieve indistinguishability, but this is certainly a very straightforward way to do it. It is the way we do it. And it does imply that we've done this funny thing to the wave function. We've added the 2 bits. And you're right, actually this is affecting the particles in a way. It's not directly saying there's an interaction between them. If that's what you meant, no, it's not saying that, okay? And in fact, your question was timely, because I'm about to show you sort of how it does affect them. Now, realize that, again, if I ask, does it really affect them, the question would be, well, what about a probability? And so to take a probability, and actually I'm not going to write it down. I was going to write it down. I can trivially write, the probability is this thing squared. All right? I was about to write it. I was about to write it. In fact, I will write, well, you want me to write it out? I mean, it's this thing squared plus this squared times that squared plus 2 times this times this times this times this, right? Plus this squared times that squared, right? That's what it is. That's not very illuminating. It's all that. We could take the, I could take this, this guy, right? So this should have been modified by taking that and adding to it, right? Just the reverse sine n2 pi over L x1 sine n1 pi over L x2. And then if I want the probability of x1, x2, I just square it all. I just do it, right? Okay? That's all I'm doing. Note, before I do a little more explanation, let me just note, I did follow a nice pattern, and if you don't follow it, it kind of gets real confusing. I always write x1 in the first location. So I'm swapping the states meaning whether it was like the n equals 1 or n equals 2 state, left, right. I keep the particles lined up. The first one, the second one, the third one. Okay? Okay, so that's what's going on here. This map changes though. That's what changes. So I hope this comes up. Okay, good. And it's in your book. I can't compete with the book for drawing it. So let's just use this and plot what's in your book.
Okay, how many? Uh-oh.
Can I do this? There we go. All right, that's great. So, this was, I took n equals 1 and n equals 2 before. The book, we plotted one of them, n equals 1 was 4, and n equals 2, sorry, n1 was 4 humps, 4 half waves. This is the probability which squares that. And this was the 2 was 3. And so you see this 3 by 4 pattern. That's exactly analogous to what I sketched for the 1 and 2, right? And then that's wrong because, you know, I can distinguish particle 1 has a trough here, 0 probability of being in the center, where particle 2 had the anti-trough, this maximum there. So if I follow the simple, straightforward, just plug and chug and square that thing where I've added the 2 with the sign switched, the math isn't very illuminating. What's illuminating is to look at the mathematical result, and it's the following. Okay, I'm actually, see if I can zoom in. There, ooh, yeah. Perfect. All right. This is the symmetric case. Symmetric meant just that when I reversed the particles, I got a positive sign. The wave function was identical. Antisymmetric meant when I reversed I put the negative sign in there. When I reverse it, I get a negative sign overall in a very straightforward way. And look what happened. It's just a slightly different pattern, but you see that x1 and x2, it's the same. Okay? Right? If I'm out here at x1, I see a hump, but it's the same as if I saw a hump over there. I see a big hump out there, big hump over there. It's symmetric. They're overall, I've symmetrized it between particles 1 and 2. But the symmetric and antisymmetric states, meaning this negative sign, the A state or the S state, they are different. And this is an interesting thing that I don't know quite how it's sort of, I'm not sure, it's not intuitive to me why the negative sign necessarily does that. But what's favored in the symmetric state is that the particles will actually be in the same state. That's this diagonal direction where it's quite likely that either will be in this, they'll both be in this first hump or they'll both be in that last hump. It's very disfavored that particle 2 would be in this first hump while particle 1 was what for it is the last hump, right? This is the origin. So here's 2 near the origin, but 1 away from the origin. Whereas the antisymmetric state, where I'd put the negative sign in mathematically, it's likely that one particle is out here near L while the other particle is near 0, and vice versa. So so it did affect the particles. Okay, that's the answer to your question. It did not affect them through an energy. It did not affect them through a potential, which meant a force. this bizarre assertion that I need to distinguish them gave me sort of two possible ways that I can mathematically scramble them. And the two mathematical ways that I can scramble them amounts to two tendencies. One is a tendency for the particles to sort of occupy the same spatial state. Because remember, again, this is drawn as a two thing, almost like xy, but it's not. It's just the independent probability for each of them just to have an x value, okay? So I either put them in where they like to be in the same state, or they like to be in a different state. And that's qualitatively important. This is not mathematically hard, but it is qualitatively important because it underlies much of chemistry. And it's very fundamental in quantum mechanics. Because, after all, we very rarely deal with a single particle alone. And we need to think about how we combine particles. Okay? So, okay, that's that. Okay. Now it turns out, I mean, I hope you've been reading the book, and so this won't be a surprise, but you might ask, I was doing angular momentum, and I had, we did L and S and J, and now suddenly I start talking about two particles and their symmetry and antisymmetry. You might say, well, why in the world are these in the same chapter? Why did I do them in subsequent days? Okay? Well, the reason is I now have to tell you something else about the quantum mechanical world, which is simply, more or less simply an experimental fact. If you will, it's just a postulate. It can be derived from some other postulates, but it is a fact, or it's based on postulate. It's not something I can derive. So in addition to the idea that particles are distinguishable, it turns out that fundamentally, whether or not a state can be two particles can occupy this type of state versus that type of state is a fundamental property of the particles. Some get to do this, some get to do that. And whether they get to do this or that depends on their spin or their angular momentum. Why is this? It just is. So do you guys know which particles get to occupy these? Does anyone know? Do what? They're the same spin. Oh no, wait a minute. Let me back up a second. I might even just mean that state one is simply the spin state. Okay? I'm going to include the spin, like an L state is part of the label 1 here. Okay? But I mean a little bit different. I'm saying it turns out, so if you have one type of spin, and now but here I mean the intrinsic spin, or J, then you can construct for the two particles this type of state that's symmetric, and for a different type of particle you have to do this state. So do you guys know or not know?
Like electrons being the different?
The electrons are in the different, but what was it about the electron that made it the different, the antisymmetric? We're working up to the Pauli exclusion principle, yeah, but it fundamentally depended on something about the spin. Whether the spin was integer or non-integer. So, I think this is kind of neat and cool, but it's just like, it's a bizarre thing. It's whether or not the spin is an integer or a half integer. Okay, and that's just reality. So, let me write that down. If the spin is half integer, now, in fact, the most famous half integer of all is simply 1/2. Okay? So s equals 1/2 is one example. However, if there were s equals 3/2 particles, it would apply to them. But it's not that simple. complicated systems, an electron in an overall state where its L and its F's combine to give it a J. And remember I belabored the fact that J is now the good quantum number? Why did I care about that? Because whatever it is the overall angular momentum is what this comment applies to. So an electron in an atom acting like a J equals 3/2 state will apply then, okay? So it doesn't have to just be, if electrons alone, it's simply a half. But if it's got an angular momentum, then you're going to combine it. You're going to think about that overall thing. So if it's a half integer, then it's antisymmetric. And that's really profound, because what happened with the antisymmetric particles? Well, the thing I just drew, they don't want to be in the same spatial location. If I put two of them in a box, they run away from each other. Yeah?
Well, aren't protons and neutrons have spin?
Yes. It's not just electrons. Protons and neutrons have the same behavior.
They're all like in nucleus together.
But they're not in the same ground state. And as we will do later in the semester, if they were, we wouldn't have nuclear fusion. Okay? Or we wouldn't have nuclear fission, for sure. We'd still have nuclear fusion. Yeah?
So does this suggest something about if you put a proton and an electron in a one-dimensional box?
No. A proton is distinguishable from an electron.
Okay.
Two electrons are not distinguishable from each other. So I have to have, as I said at the beginning, electrons, protons, Siamese cats, whatever it is.
Okay.
All right? And there's a word for this, and it's called fermions. After the great physicist Enrico Fermi. Okay? If the spin is integer, so this could be s equals 0, 1, 2. So a non-spinned particle, or a photon, which is a spin 1 particle, or a graviton, which is a spin 2 particle, or an electron in an atom in well, no, an electron, okay, sorry, let me back off. If you have, for some reason, a particle in a J equals 1 or 0, integer J state, okay? Then it's symmetric. And this is called a boson. It's always a funny name. Named after the guy, the speaker person, Bose. No, there was a great Indian physicist, Bose, B-O-S-E. And they're named after him, bosons. Okay? And so this is just an interesting additional wrinkle on everything else we've learned, is that spin 1/2, and that's all the fundamental particles we ever deal with, electron, proton, neutron, and a neutrino, the stable particles that we know of, unless there's dark matter as a particle. That'll be the fifth stable particle we know of. They just do this. You put them together, and they try to go somewhere else. Let me give you an extreme example of why. I mean, I wish I could have written down a formula that showed that that graph, the graphs I showed where the antisymmetric state, the particles were separated. If one wanted to be at the L equals 0, sorry, if one wanted to be near the origin, the other one wanted to be away from the origin. That was essentially what those lumps meant. And go look at your book and stare at that a minute and make sure you understand that. I wish I could write a formula for that, but there's not really a formula for it. But look at this most extreme case. What if states 1 and 2 are the same? The notation I've chosen fails a little bit here. I was saying, you know, there's a state for the first particle and a state for the second particle. I'm saying, what if they're in the same state? In other words, what if I had the overall wave function equal to psi 1 of x1 times psi 1 of x2? I mean, that's perfectly fine. Let's put two particles in a box, and let's put them both in the n equals 1 state. Okay? I can go ahead and I can add the same thing again, reversing 1 and 1, but of course that doesn't do anything. So that is the symmetrized wave function, right? I've gone through the procedure of adding the second term. It's just that the second term was identical. It gave me a factor of 2, and I threw that away. All right? So that's the symmetric state. The antisymmetric state, though, is what? It's psi 1 of x1, psi 1 of x2, minus psi 1 of x1, psi 1 of x2. It is 0. All right? There is no symmetric state. There is no antisymmetric state for the particle being in the same state. Right? It just doesn't exist. It's 0. Just mathematically, it is 0. This was clearly the state that tried to make the particles be the same. Or more, put it, in more sort of intuitive terms, this was the state that tried to put the particles in the same place. Put them both in the same hump. Okay? If I try to do that for the antisymmetric particles, it vanishes. This is called the Pauli exclusion principle. Okay? The fact, if you will, instead of calling it, instead of just making some rules for the Pauli exclusion principle, the Pauli exclusion principle is the result of the fact that the way to anti-symmetrize a multi-particle system is to take the particle, subtract it, and then add it again with the, take the product state and subtract the product state with the two states reversed, okay? And then that, by definition, this construct has to vanish if state 1 and state 2 are the same, which is simply to say you can't put two identical particles in the same state. That's the result of it. So if you will, I derived the Pauli exclusion principle, but from this bizarre set of assumptions. And I imagine you guys have heard the Pauli exclusion principle, named after Pauli, German physicist, one of the founders of quantum mechanics, along with Fermi, others. All right? And what's interesting is it amounts to a force, if you will. All right? If I stick one electron in a particle in a box, and I try to stick another electron in the particle in the box, what has to happen to that second electron? If the first electron went into the n equals 1 state, then the next electron has to be in an n equals 2 or 3 or 4 or whatever state. So the second particle that goes in has to be at a higher energy. And so the system has to have more energy, period. And it's as if, like, the first electron had a force which kept the second electron away from it. So while the first electron was in the n equals 1 hump, it forced the second electron to be on the edges in the n equals 2 state. And it amounts to a force. And people actually, not very often, but in times they'll even talk about an exclusion force. Because it really matters for how an atom, for chemistry and how atoms are put together and everything. Yet there is no force associated with it. There's no potential, there's nothing. There's just this notion of the indistinguishability of particles, and this bizarre thing that depending on whether a particle's spin, who knew that a particle had to have this fundamental property of a spin? Given that we think they're point-like and it's not even really clear what in the world the spin meant, given that the spin is something that seems like it's spinning but it can't slow down, so it's just a sort of fundamental rotational thing, given that abstractness that is concretely real but is still weird, why did it care? Why did nature care that it was half integer or integer? But it does in a fundamental way. If I stick photons, say, in a box, I can stick them all in the ground state. They have spin equals 1. They don't have this exclusion principle. If I stick 1,000,000 photons in a box in an infinitely deep well, they're all in the ground state. And my energy is 1,000,000 times that ground state energy. Okay, if I stick 1,000,000 electrons in a box, the last one that went in is in the state of 1,000,000, which is a very, very high energy. So a box of electrons has enormously much more, a box of fermions has enormously much more energy than a box of bosons. Okay? Fact. I guess we'll stop there. Okay?